Good morning, welcome. Today, we are going to introduce weighted graph in chapter 29. In the preceding chapter, we studied modeling graph, and we look at the graph. The graph is unweighted, so we just have vertices and edges. Now, this time, we are going to assign weights on the edges. So here, let's look at this diagram here. Now, we're very familiar with this diagram. So this is the graph of the cities and the edges connecting the cities. Now, we assign the distance on the edge. So here, from Seattle to Chicago is 2,097 miles. So, and we assign the weights. So the weights are distance. We're going to ask the questions, how do you find the shortest distance from one city to the other? So any two cities, and can you find the shortest distance between the two? So from Seattle to Miami, and what is the shortest distance? So look, this is, we have only limited number of vertices, and you can look at it and figure it out. But if you have a large number of vertices, and you need to have an algorithm and develop program and to solve the problem. So this is what you do when you go to look at the Google map and you want to find the best route. You consider many factors and you get the best route. So that's essentially the algorithm behind the Google map. So here we are going to ask this question and the shortest distance. So first thing we're going to do is to model the graph, the weighted graph now. We already have the unweighted graph. So the weighted graph, it's just going to becoming a subtype of the unweighted graph with additional property that is the weight. All right, so we're gonna see how we're gonna look at some of this typical algorithm for weighted graphs, and you can look at the animation here. I can add a new vertex and add edges, and we can add another vertex and add edges. So this is here, and see let's see, we're gonna find the shortest path between vertex 2 and 5. So we're gonna find the shortest path. Okay, so this is the shortest path. Click on this button, shortest path, and you're gonna see the shortest path is displayed. All right, so now let's look at the how we're gonna model weighted graph. So we're gonna design data structure, and in object-oriented design, and you design data structure, it is to define a class, and from the class you can create the data structure objects. All right, so I'm going to copy and paste, and with another, see, I'm going to have this is another tab. So here is another tab. Okay. And I'm going to copy and paste, have another tab here. All right, so this is another tab here. All right, so we're gonna have another tab here now, and we're gonna look at representing weighted graphs. Okay, so I think I'm going to use, okay, this. All right, so now representing weighted graphs. The vertex is the same as before. You can just use an array list of vertices. So here for the edges, and there's a couple ways we can represent it. And one is you can still use a two-dimensional array. So with the vertices, and from this is 0 to 1, and so the edge and there's a weight, it's the here is 2. So and here is 0, 1, the weight is 2, and 1 to 2, and so here's 1 to 2, and the weight is 7. So you can write this. All right, this is not always going to work, because what happens, your weight is not an integer, so you cannot write the code like this, and so it's not going to work with the weight of non-integer type. All right, so what we can do is you can have, instead of use this int brackets, and you can use object brackets. In this way, you can have, so here is integer object for indices. It's index 0 and to index 1. So there's age. And then you can put this is the weight. It's some kind of type for the weight here. All right, you can also have the weighted adjacency matrices. So this is here, you can put the width in the matrix and as a value here in the matrix. So here is from 0 to 1, and the value is 2. And from 0 to 3, the value is 8. So, all right, and now the best way we're going to do it, the most flexible way, is to define a weighted edge class. So here's weighted edge class extends age. All right, so we need to be able to compare the weights in all the weighted graph algorithm. And because we could look at the weights, so we need to compare the weights. So it's very common, so we're going to implement. So we're going to have this weighted edge implements, and this is java.util.comparable with another weighted age. All right, so here we're going to overwrite the compare to method, and we're going to compare to weighted age, and we're going to have this is we're going to compare this is the one, this weighted age with another one. So the other one is called, this is just called, this is age. So here is, it's like this dot weight is greater than age dot weight. So we're going to return 1, it's positive, and here is going to return 0 and equal, and otherwise return -1. So this is a constructor. You construct a weighted age, UV. All right, so here we have a weight. So look, how do you do this? And we're going to have this extends age. So we're just going to invoke a super dot. This is the constructor super, and go into super constructor U and V. So that's age. So this way. All right, so that's weighted edge. Weighted edge now is a subtype of edge, and edge is in the unweighted graph. So you can consider that unweighted graph is a general graph, and this weighted graph is a specialized graph. All right, and now we're gonna have this is the all this neighbors, and you have this neighbors and with all this weighted edges, and you have the width there. So this is the adjacent edges here, and for all the neighbors and all the adjacent weighted edges. All right, so now I'm gonna go to the next. I'm gonna go to this 29.3. So we're gonna design this weighted graph as a subtype of unweighted graph. So unweighted graph is a subtype of a graph. So look at the UML diagram notation. So this is inheritance, and here is the interface inheritance. So this is notation. It's a dash line, and it points to this interface. So we have all these constructors. The many different ways you can construct a weighted graph. And so these are the methods. You can print all the weighted edges and get weight between an edge. So this is two vertices, okay? And add a new edge. So here's get minimum spanning tree. So this is the, we're gonna get shortest path. So this is very common. We're gonna study here is minimum spanning tree. So what is the minimum spanning tree? We're gonna talk about today later. Okay, so what's a minimum spanning tree? All right, the class weighted graph, and here extends unweighted graph. So here is the generic type is this vertex V. So this is the all the constructors and all the constructors. And let's look at this one method here is you have add age. So how are you going to add age? So you're going to do this. It's simply you can call this is super dot add age. And using this, you're going to create a new weighted edge. U, V, and weight. So using this weighted edge, we just have this and invoke this add age. Add age in the weighted graph, in the unweighted graph, that's the age object. So here, weighted edge is a subtype, so we can put it like this. Okay. All right. Now, see, if you go to I'm going to open another tab and to look at the code for the add age in the unweighted graph. So here, I'm going to look at this, add this. So here is this is the modeling graph. So we can look at this modeling graph. You can see this right here is this one right here. It's unweighted graph. Look at this at age. I'm gonna do this answer here. Now you can see this is at age is right here. So here at age. All right, you see at age? It is this. There's one. There's another. So there's at age. It is the overloaded methods at age. Okay, so this is the add age UV add 1. So you add age new age UV. So here, this one is at this age right here. So for this, what it does is you're gonna add this age E to the adjacent list for the neighbor of E dot U. So this edge, there's two vertices, EV, E dot U, and E dot V. So we only go with this is U from U to V. Consider this as one direction, U to V. So this is one, it's added. All right. There is an error in the quiz. So I want to point to you. It's right here. So let's go down to, I'm going to open a, all right, just go to the next one here. It's the, so maybe I should just do another tab, duplicate tab, okay. Okay, so the student discovered this error, and thanks for the correction. So this is the quiz, 29.3. All right. So here the add age UVW method performs the following operations. So here, this should be true. Invokes super dot at UV to add age. Actually, this is not. Actually, no, I think it's. It's just no. Okay, I got it. I think what happens is this. This is really wrong here. Pre-select all that applies. So there's only one single choice here. So there's only one single choice here. So invoke super dot at UV. So that is not right. So if you go put it back here, invokes. So here this will be wrong. So if you say at UV, it is wrong. That's not. You don't have the. No, I'm sorry. This is correct. This is the one. I'm looking at a different. Just be careful here. This one is in unweighted graph. Okay, so this is unweighted graph. Okay, all right. So here, unweighted graph. All right. Okay, so this is unweighted graph here. Okay. All right. So now this is the weighted graph. For the weighted graph, this is what we need. We have to have the weights here. So if you just say, hey, new, you're going to do add age, call this add age UV, it's not going to be correct. So if you say, I'm just going to say add this UV here. No, you're going to lose the weight. Weight is not there. So you have to use this. Okay, this is the one. All right, I'm coming back here. You're going to see this. Invokes super dot at this UV is incorrect. All right, so here adds a weighted age to adjacent list for vertex U. No, this is the one here. Adds a weighted edge to the adjacent list for vertex U. It's correct. So invokes add age method defined in the unweighted graph class. This is actually right. Both of this are actually right. So actually, so this is both right. So I think the so you're going to see this one is directly. You're going to see the add age method. So here we have the add edge method here. This is for the weighted graph here. So this one here is weighted graph class here. So here, this is the add age. Okay. And this one is also correct indirectly because it adds a weighted age to adjacent list for vertex U, it's because of this right here. So you invoke add age. So this is right here. And this is the add age for this age right here. And this is, you are going to add it right here. Yeah, you're going to add it right here. You're going to add it right here, add it right here. Yeah. All right. So the correct answer should be both. Add a weighted age to the adjacent list for vertex U, and here invokes this add age method defined in unweighted graph. Both, but there's a mistake here in this multiple choice quiz. I think it only accepts this as the correct one. It didn't accept this, so let's try it now. Yeah, so that's the one here. It only accepts this as the correct one. Okay, so we're gonna have to fix it. Have to fix it, but we cannot fix it now, so we just have to accept this mistake now. All right. So let's go back to this code here. Its implementation of this is straightforward and except these two methods: get minimum spanning tree and get shortest path. So this is what we're going to do now. But first thing we're going to do is to look at the so minimum spanning tree here. So we're going to do a minimum spanning tree. Okay, and then we're going to do the shortest path. Okay, all right. So minimum spanning tree. All right, minimum spanning tree is a subgraph from the weighted graph. The subgraph consists of all the vertices, but it's going to be a tree. Okay, so the subgraph is a tree. So what is a tree? In the tree, you do not have a cycle. In a tree, it's basically the number of vertices is one more than the number of edges. Okay, so if you have a tree here, you have 3 vertices and you must have 2 edges. If you have 4 vertices, you have 3 edges. So that's, and there's no cycle. Okay, all right. So here's the example. We have this graph, vertices, edges, and width on the edges. So what's a minimum spanning tree? All right, this is one example. This is a spanning tree. So look at the spanning tree here. Is you have all the vertices are connected, but there's no cycle. Okay, so that's a tree. And what's the total weight? You add all this together. So this is 10, 5, 7, 5, 7, 8, and is total is 42. All right, so that's one. All right, here's another one, is C. Okay, so this is also a spanning tree. The total weight is 38, so it's better than the previous one. Now, there's another one here. It's also a spanning tree, and this spanning tree has the weight is the same, 38. All right, you can prove that in this example, the minimum spanning tree has the total weight of 38. So this is the minimum. All right, a minimum spanning tree has a lot of applications. Just think about it. You're going to build a telecommunication system connecting all the cities. You're going to lay out the fiber communication. You want to have the minimum cost to connect all. So that is going to find the minimum spanning tree. So you just consider distance, okay? So the more distance, the more cost, all right? So you want to minimize in all the distance and to save the cost. And so that's a minimum spanning tree. All right. Okay. So this is really actually a simple graph. You're going to take some time to find the solution and for a minimum spanning tree. So one thing you already noticed that minimum spanning tree is not unique. Like this C is a minimum spanning tree and D is also a minimum spanning tree. And all we need is just to find the one. We're going to find one minimum spanning tree. All right, we're going to develop algorithm. So here we have this model here, the graph model. We have the vertices, edges, and the weights. And we have all the data now in this graph object. And we're going to have an algorithm to find the minimum spanning tree. All right, so the minimum spanning tree here is the algorithm. And we are going to have, this is MST, the minimum spanning tree. The minimum spanning tree is going to be a subset of our search tree. So you have you're going to start from a vertex to find the minimum spanning tree. So that starting vertex is now the root in the minimum spanning tree. And then all this and all the other votes, you have the parents, okay? And the root does not have a parent. So we're going to have, this is the minimum spanning tree and with non-negative weights. All right, so we just want to make sure there's non-negative weights. And with the negative weights, it's not going to work. So it's just assume this is all non-negative weights. And this, we're going to have a minimum spanning tree with vertex S as the root. So starting vertex. So this is the S right here, S. Okay. So let T be a set for the vertices in the spanning tree. Initially, it's empty. There's nothing. So we're going to have this T. Look at this T right here. It's initially, no. You're going to keep adding it into the T. So here is V minus T, all the vertices. If this T is empty initially, so you have all the vertices right here. Okay. All right, initially, you're going to add the starting vertex S to T. So we're going to have S to T. Now, then you keep adding it. All right, so here, while the size of T is less than N, all right, so you still have more vertices to add into T. So we're going to find X in T and Y in V minus T with the smallest weight on edge XY. All right, so as shown in this diagram here. So here, we're going to find this X and Y such that this edge is the smallest. So we're going to bring Y into this T. All right, we're going to move it. All right, so you move it and look, this is how you're going to move this Y, it's here. So Y has this connection here. So now, and it's moved right here. So, and why you move this? Because this is the smallest among all these edges connecting T and V minus T. So that's how you're going to describe your algorithm. You're going to use we're going to find this x, so this and in t and y in v minus t, and with the smallest weight on the edge, x, y. So we're going to now add y to t and set parent of this y is x. X is now parent of y. All right, keep doing this. Eventually, you get everything from this v minus t into t. So this will be empty eventually. So when you start with the algorithm, this t is empty. You add a starting vertex, then keep adding others. So this is the algorithm. Okay, it's a greedy algorithm. You're gonna see it's always you find the minimum weight among this x, y. X is in t and y is in v minus t. Add it. All right, so this is the algorithm. We're going to do some adjustment and refinement for this algorithm now. So the things we're going to do is, I think I want you to look at this diagram, see how this works, this algorithm works. This is the diagram. We'll show you the steps and how all this works with each initial state, okay? And then you keep adding it. So this, all eventually you're gonna add everything. All right, and now I'm gonna refine it. So this is refining the minimum spanning tree algorithm. And the minimum spanning tree algorithm we just presented, it's called PRIMS. So it was invented by this person and PRIMS. So he gets a name and call this is his algorithm, a PRIMS algorithm. So we're gonna have just refine it. So the way is this, we're gonna slightly refine it. The reason we need to refine it is this part. So how you do this efficient, how do you find this x, y? We need to do a little more, put more work on this x, y. So how do you find this h? That's really the key part. All right, so to facilitate this, we're going to introduce additional data structure here. So the additional data structure we're going to introduce here, use the cost v. So we're going to have every vertex, we're going to have associate this with a cost. And this cost v is to store the cost of adding vertex v to the spanning tree. Okay. All right. If this is the minimum, we're going to pick whichever is the minimum. So that's going to become easy. All right. So just look at each vertex. Who has the lowest cost? Okay. Now, initially, and the cost for the starting vertex, S is 0, right? That makes sense. It's 0. Okay. And for starting vertex, you're going to assign infinity cost v to all the other vertices. Okay. So here is the refined algorithm. All right. So the refined algorithm is now we're going to have this the same as T is a set that contains the vertices in the spanning tree. Initially, T is empty. And now we're going to have assign the cost for all. S is 0 cost for the starting vertex, and all the others are infinity. All right. So for y size of T is less than n, find U not in T with the smallest cost. This is easy now. It's really easy done. Just the array. You compare all this cost, then find it. It's not in T yet. So we're going to add to this U to T. Now, after you add it, you do have to do some adjustment on the cost. So each V not in T and UV is in E. So if the cost of this V is greater than this WUV, all right, and then you have a smaller one, so you need to adjust it. And at the same time, you adjust the parent. So that's here. If you go look at the diagram here, all right, so this we find this y is the smallest, this cost y is the lowest. So that's why we move y here. Now, when you move y here, you have to adjust the cost of this two. Their cost may change. So these two vertices here, this one, all right, and this one. So this two and their cost may change. All right, so that's here. What we are doing, it's right here for this adjustment. All right, with this and the algorithm, it's really easy to implement. So before we do this, I want to also point to you this MST. What is MST? MST, we're going to make MST as a subtype of the search tree. So it's a weighted graph.mst. It's a subtype of the search tree. In this MST, we need to add additional feature, is the total weight. So that's useful. And we need to have this get method, get total weight too. All right, the constructor, you can have a root, you have parent, you have a search order, and plus a total weight. All right, so here, this is the algorithm. And now we can go to look at the implementation for this. And this is the implementation now. So we're going to look at the implementation now, and you're going to see this here. Minimum spanning tree. Look at the minimum, get the minimum spanning tree. So if you invoke this method, and that's by default, it's starting from the vertex with index 0. All right, and then you can have this is the starting. Okay. Starting here. All right, it's a starting. Vertex. Okay, in the algorithm, we call this as S. Okay, but this is starting vertex here. The cost, okay, and so it's array. It's real simple. Double, and what is this? How many vertices here? It's the size. All right, so please note that, and this, the size, the graph. Okay, I think it's get size. Okay, so let's get size. All right, and then now initial cost. Hey, how do you write this? All this infinity. How do you write this infinity here? Infinity, you can have this double dot. There is, I think it's a max something. Not sure. This is the, I think it's called max value. So I'm going to do this. It's in the API. You can get that max value here. All right, see, this is positive infinity. Okay, so here, this is the there's a positive infinity here. Using that. Okay, there's one. It's positive infinity. So in the API. Oh. All right, here, positive infinity, double dot positive infinity right here. All right, starting vertex and 0, and now you get a parent and get the so parent of starting vertex. It's set this to -1, and means this is the root, and total weight is now it's 0. So we're gonna get the list. This is going to be the search order. So here it just corresponds to the algorithm, the while loop in this algorithm. So here in the while loop of the algorithm, so this is how we do this. All right, so please have this and two things. It's the implementation and algorithm, put that side by side. So when you study it and you see how it is implemented. And eventually we're going to return, this is the one here. Minimum spanning tree with a starting vertex, parent, T, and total weight. Okay. All right, I'm gonna stop here. We're gonna continue to pick up and the rest of this minimum spanning tree next time. Any questions? Any questions? Yeah.
Oh, no questions.
All right. Thank you very much. And see you next time.
Have a good one.
Bye.